Standing waves are really important in how sound is created in many musical instruments. They happen when a wave vibrates in a space, often fixed at one or both ends, like a guitar string stretched tight or air trapped inside a flute or organ pipe. These waves only form at certain frequencies that fit just right within that space, and these frequencies are called resonant frequencies or harmonics. The images show this idea with a guitar and a pan flute, illustrating how the waves move and create the sounds we hear. Understanding this helps explain why instruments sound the way they do.
When two waves with the same frequency and wavelength travel through the same medium but in opposite directions, they can overlap or superpose. For this superposition to create a standing wave, the two waves must also have similar amplitudes. This interaction results in a wave pattern that vibrates in one direction but has no transverse linear motion, even though it's made up of two waves moving in opposite directions. The key factors are the identical frequency and wavelength, the matching amplitude, and the opposing travel paths of these waves, all combining to form this unique wave structure.
Standing waves are commonly formed when a wave hits a boundary and reflects back. The original wave moving toward the boundary and the reflected wave moving back interfere or combine with each other. This interaction is called superposition. When the reflection happens at a fixed end, the wave undergoes a phase change of 180 degrees, or pi radians. This phase shift is important because it creates a point called a node right at the boundary, where the wave's displacement is always zero. This process of reflection and interference explains how standing waves form and why nodes appear at specific locations along the wave. Here, we can see the basic structure of a standing wave, which consists of nodes and antinodes. Nodes are the points where the wave has zero amplitude, meaning no movement occurs there because of destructive interference. In contrast, antinodes are points where the amplitude is at its maximum, caused by constructive interference. The distance between two consecutive nodes or antinodes is half the wavelength of the wave. Additionally, all points between two adjacent nodes move together in phase, meaning they oscillate simultaneously. This pattern helps us understand the fundamental behavior of waves and their interaction in various contexts. Standing waves are different from traveling waves because they don't transfer energy from one end of the medium to the other. Instead, the energy is confined within specific regions called loops, which lie between the nodes. Within these loops, energy keeps shifting back and forth between two forms. It reaches its highest potential energy when the string is at its greatest displacement, which happens at the antinodes, and reaches its highest kinetic energy when the string moves through the equilibrium position at its fastest speed. This constant oscillation between potential and kinetic energy is what characterizes the stored energy in standing waves.